We will use the bigO notation to express the time complexity of an algorithm. We have already seen how to determine an execution time function for an algorithm. But when determining the execution time function, the problem is that depending on how you count instructions, you might get different functions. However, all the different functions one gets will have the same growth rate, and that's where the bigO notation comes in. The bigO notation expresses the growth rate of a function. To be more exact, the bigO notation gives an upper limit of the growth rate. If you look at the growth rate of a function, then constant terms and constant factors do not matter and can be dropped. For example, the function f of n equal to n squared and g of n equal to 3n squared plus 4 have the same growth rate. Let's define bigO. Remember that bigO is defined for functions in general, not only for execution time functions. In fact, the bigO notation was introduced before the invention of modern computing in 1894 by Paul Bachmann. Assume we have two functions, f and g. The definition specifies a condition when f has the same or a lower growth rate than function g. In that case, we say that f is bigO of g. So when is f bigO of g? The definition says there must exist two positive constants, c and k, such that the absolute value of f of n is less than or equal to c times the absolute value of g of n for all n greater than k. In other words, if we can multiply g with the constant c, possibly a very large constant, such that c times the absolute value of g of n is greater than or equal to the absolute value of f of n for sufficiently large values n, then f of n is O of g of n. The graph on this slide shows two functions, f and g. Note that the actual value of f is greater than the value of g, at least if the argument is greater than 0. But although the value of f is greater than the value of g, both functions grow in a linear fashion and therefore have the same growth rate. We can say that f of n is O of g of n, so g is an upper bound of the growth rate of f. Similarly, as in the previous example, two quadratic functions have the same growth rate. The constant factor 2 in the function value of f of n can be dropped, and the constant 1 that is added can be dropped as well as far as the growth rate of f is concerned. So f of n is O of g of n. In general, a constant multiplier can be dropped. That is, a function c times g of n is O of g of n. Note that c must be a constant and cannot depend on the value n. For example, 5n cubed is O of n cubed. If we add a constant term c to a function f of n, then the function grows the same rate as f of n without this term. Thus f of n plus c is O of f of n. For example, n cubed plus 8 is O of n cubed. These two rules can be generalized to the following rule for polynomials. If we have a polynomial like 5n cubed plus 2n minus 6, then as far as the growth rate is concerned, only the term with the highest degree matters. In this example, only the term n cubed matters. Thus, 5n cubed plus 2n minus 6 is O of n cubed. In general, a polynomial in n with degree k is O of n to the k. Here's another useful property. If f of n is O of g of n, and g of n is in turn O of h of n, then f of n is O of h of n. For example, it holds that 4n squared plus n times root of n is O of 4n squared, and 4n squared is O of n squared. Therefore, we can conclude that 4n squared plus n times root of n is O of n squared. So in future, we will express the time complexity of an algorithm in terms of the bigO notation of its execution time function. Let's assume you determine the execution time function of an algorithm to be t of n equal to 5n cubed plus 2n plus 8. Now it's always correct that a function t of n is O of t of n. So the algorithm has a complexity of O of 5n cubed plus 2n plus 8. Applying the previous properties of bigO, it also holds that t of n is O of n cubed. So we can also say that our hypothetical algorithm is O of n3. Which bigO expression should you use? Well, you should pick the most simple expression, which is n cubed in this case. Now recall that the bigO notation is an upper limit of the growth rate. The function t grows less than n to the 4, and therefore it is also technically correct to say that t of n is equal to O of n to the 4. However, one of the purposes of the bigO notations is to give a performance guarantee. You typically want to show how good your algorithm is, and a time complexity of O of n to the 4 looks much worse than O of n to the 3. So you want to find not just any upper bound for the execution time function, but preferably the lowest possible upper bound. So in our example, if you determine that the execution time function is 5n cubed plus 2n plus 8, you would say that the time complexity is cubic, that is, O of n to the 3. In many cases, the previous properties of bigO are sufficient to determine the most simple bigO expression of an execution time function. But there are some cases where the following rule might be really helpful. To understand the rule, you need some calculus knowledge. In particular, you have to know how to determine the limit of a function. Let's say you think that f of n is O of g of n. In other words, you believe that f of n grows the same or slower than g of n. You can look at the fraction f of n over g of n. If both functions have the same growth rate, then the fraction will converge towards a constant value if n gets larger. If g grows faster than f, then the fraction converges to 0 if n gets larger. So if the limit of f of n over g of n as n approaches infinity exists and is a real number, then f of n is O of g of n. You can apply this rule in most practical cases. If the limit does not exist, the rule does not help to determine whether f of n is O of g of n. Most algorithms, but not all, fit one of the standard complexity classes as listed here. I will often say that an algorithm is quadratic, for example. That means that the execution time function of that algorithm is O of n squared.